Hello everyone, and this is the third video about the local level model. In this video I'll just do some practice. In particular, I'll do simulation, so we'll draw random samples from the local level model, and after simulation I'll do inference in Python, so we'll fit the local level model to some data. In this case, I have downloaded Apple prices. I don't recommend using the local level model for stock prices, but it's just test data. So this said, let's see how it's done. First of all, let's start with simulation, right? The libraries that we are going to use are NumPy and pandas, so we import NumPy, and since we are going to do recursions, I'm also using Numba to improve speed. It's not really necessary because we won't do big loops, but it's just to show you that if we have recursions, it's a good idea to use it. If you are looping the same thing many times, it's not our case, so it's kind of useless in this case, but it's just to show you it to you. If you're interested in the library, you can check it. So to simulate the model, we have to set the parameters. So we set the parameters, right? And in our case, the parameters are sigma eta and sigma epsilon. So this value is just it's just a choice, right? You can decide which kind of value you want when you I just want to draw a sample from this model with these parameters, right? So I also want to compute the signal to noise ratio. What is the signal to noise ratio? Is a quantity which resumes the stochastic properties of our model, and you can interpret it as the strength of our desired signal with respect to the strength of the undesired signal. So the desired signal is our state, right? We want to estimate the state, and the strength of the undesired signal is the noise, right? It's the strength of the noise that we have when we take observations. So how do we compute it? We just take the variance of the state, right? And we divide it by this variance of the noise, sigma epsilon squared. And there are over two parameters that we need to initialize, which are the expected value and the variance of the first state. So we set a1 equal to 1 and p1 equal to 1. Again, it's just a choice. We can go on, we can simulate eta, right? We want we simulate 50 observations, right? Just a sample of 50, and the same goes for epsilon. And we also want to get the first state, which is just right. I'm sorry. So p1 is variance. It's not really needed to take the square root, but just to be concise. And at this point we can write the function to get our simulation. So we need to write the recursion, we just need to write the observation equation and the state equation. So I'm using numba here because we want to do a recursion, right? This is a decorator, and we define simulation. What we need to run the simulation, we need eta, epsilon, and state 1. Okay, so first of all, define the length of our simulation. We set the memory, so state is equal to n dot empty n, and observations is equal to np dot empty. And at this point we can start the recursion. First of all, we set state 0, which is equal to state 1, and we can run a recursion for for t in range n minus 1. We have state e is equal to we have observation e is equal to state e plus o plus epsilon e, and then we have the state equation, so we update the state. So the state t plus 1 is equal to the state in t plus eta t, and we also fix this one. Okay. To compute the recursion, observation n minus 1 is equal to state n minus 1. So this should be enough to complete our simulation. So we can return state and observation, right? This is our function, and we can store state and observation in these two variables. And we need eta, epsilon, and state 1. Let's run. We got an error. np dot random, right? Everything works, right? State 1 is expected to be, yeah. So perfect. So everything works. State, so it's our state vector, and observation is our observation vector. Perfect. So in this way we have simulated our model. Maybe we want to visualize like our samples, right, from the local level model, and to do so, just to make it fast, I use pandas. It's faster, so I use pd.series state name equal state dot plot legend equal true, and pd.series observation name wall observation I also want to print the signal to noise ratio, right? Print Q just to like check how maybe this way it's a bit better. Let's see if it works. Yeah, perfect. So what we can notice from the plot is that our state, right, it changes over time randomly, and our since our strength of the noise, our variance, our sigma epsilon squared, it's way higher than sigma eta squared, right? So what we observe is this, like, it's really different from what we actually care about, right? We have a really high disturbance. That's the idea of our signal to noise ratio, right? It's really low because we have really low signal with respect to our noise. If we, for example, changed the values, right? If we use 100 for sigma eta and 10 for epsilon, we'd get the opposite result, right? We'd get that basically, right, the error is extremely low, and our observation is really close to the state. So now I want to show you something else, and I want to show you that there is a link between the local level model and the ARIMA 011 model, right? So the local level model in most cases has a ARIMA 011 representation, so I can kind of show you. I'll just show it without proving it, right? So to check this property, first of all, I want to compute the theta, right, the parameter of the ARIMA process. We can compute it using this formula, 0.5 minus 2 minus Q plus NP. So okay, this is the formula. If something is wrong, we'll notice it. And at this point we can compute sigma xc. Xc is our error in the moving average process, right? And so sigma xc is computed using sigma eta divided by 1 plus theta. At this point we can simulate xc, and I used 5,000 observations, and I want to use 5,000 observations here too. So again, to simulate a moving average process, I want to use a recursion, so I use JIT. This is not necessary when we are dealing with only 5,000, but again, it's just so we just need xc and theta, right, to simulate a moving average process. And to do so, we start by allocating the memory. So and then we can loop. Again, I'm used to using I, but maybe it is better. It's equal to c t plus 1, so it's our error plus theta multiplied by c in time t, right? So this is just moving average one process, right? And we can return series. So now we can just get move average, like I just call it at ma1. So we need c and theta, we already have them, right? We have computed them before. I call it name equal ma1, and also I set ma0 to none. Okay, so we have our moving average one process with the parameters derived from the local level model parameters, and we can check if we can represent our local level model as an ARIMA process. Everything, it seems to be working. I hope so. Maybe something is wrong, I don't know, but I don't think so. So to check the property, the representation, I just plot the M1 process, right, versus the first difference of the local level model, right? So let's take the LLM is equal to PD dot series observation dot diff, and at this point we can plot it, DLM dot plot legend equal true. Maybe it's better if I assign a name here. Name is equal obs diff, and aim a1 dot plot legend equal true, grid equal true. And to be sure about the fact that it's the same MA1 process, the difference local level model have the generated MA1, we check the variance of the two processes. So MA1 dot var, and we also print DLLM dot var, and I hope everything works. Yeah, as you can see, we get two samples generated from basically the same process, right? They have the same variance, and they are stationary, and we can even check like the first autocorrelation if we want, but yeah, it's just an MA1 process. So this is just to show you in practice that the local level model in most cases has a ARIMA 011 representation, so we can potentially get predictions for the local level model just by using like the usual methods, right, with ARIMA. There is one thing I want to be specific about, and the thing is that if we use the ARIMA Box-Jenkins method for prediction, one-step ahead predictions. We get predictions for the observations while using state space models and the Kalman filter. We can get predictions for the states, right, or for the various components of the components model with components that we can build using and represent in state space form. So we have an advantage in using state space models and the Kalman filter over using Box-Jenkins. Now I'm going to code the Kalman filter for the local level model. The Kalman filter is a recursion, so I'll start by using the JIT decorator. And to define the function, so to run the Kalman filter, we need observations and the parameters sigma eta and sigma epsilon. Again, we start by allocating the memory, and we have n equal len observations, v equal empty, like it's basically the same as empty, but we pass a different argument. So we have v and f, the one step ahead prediction error and the variance of a one step prediction error. Then we have the Kalman gain. AT is the updated conditional expectation, and PT is the updated conditional variance. And then we have A, which is our one step ahead prediction, and P, which is again our one step ahead prediction. To start the Kalman filter recursion, I'll use what is called a diffuse initialization. The idea behind the diffuse initialization is that P1 tends to infinity, so we compute P2 as P1 tends to infinity, and we compute A2 as P1 tends to infinity. The idea, of course, is that we don't really know anything about the state 1 and about its distribution, and so we have infinite variance. In the case of the local level model, if we use this kind of initialization, we get that A1 in Python, which is A2, so indices in Python, right, starts from 0, is equal to the first observation, and P1 is equal to sigma eta squared sigma plus sigma epsilon squared. So this is our diffuse initialization. I'll make a video probably in the future about the Kalman filter and the exact Kalman filter, where the exact Kalman filter is the Kalman filter with the diffuse initialization, right? At this point we can start the recursion for t in range. We start from 1 because we have the diffuse initialization. We define Vt, which is our prediction error, which is equal to observation of time t minus our prediction at, and ft, which is equal to the variance of the time t plus sigma epsilon squared. And then we can define the Kalman gain at time t, which is equal to pt divided by ft. Right, so we have computed the error step of the Kalman filter. We can proceed with the update step. So we update at at time t is equal to a t plus the Kalman gain multiplied by the innovation and p t at time t, which is equal to pt multiplied by 1 minus kt. And finally, we can do our prediction step with at plus 1 is equal to at plus kt multiplied by the innovation. It's the same as the updated conditional expectation, and pt plus 1 is equal to pt multiplied by 1 minus kt plus sigma eta squared. Right, everything should be right, I hope so. Just one last thing, we have to compute the last step of the Kalman filter, right? And to compute it, we place it outside the loop. We don't need these two. N minus 1 . So we have finished our function. We can return v, f, k, at, p, t, a, and we can test if everything works. V, f, k, at, p, t, a, and p is equal to Kalman filter, and we pass the observations sigma eta and sigma epsilon. I hope everything works. Oh yeah, if we do this, of course we don't get A0, nor, which is, I mean, it's the A1 in the theory, right? This is A1, but it's A2 in the theory. So we don't have A1 and A given T1. So we don't have the first elements of AT and the first element of A, but we can just set them like we can choose them. So I'll just set A0 is equal to observation 0. This is just a choice. So we can run this again. and everything seems to be working just fine. So let's check with a graph, right? So let's check with a graph. 80 equal pd dot series 80 name equal prediction Kalman filter. So we can plot it. 80 dot plot legend equal true and state, right? We still have our state dot plot legend equal true. Oh, of course we have to do, right? pd dot series state name equals state. So we have our real state from the simulated model, and we have the prediction of our state. We can see the differences, right? And as we can see, the predictions are quite good, right? This isn't surprising given that everything is Gaussian, so everything is perfect for the Kalman filter. So this video is getting too long. If you managed to finish the whole video, congratulations. And I'll do a second video, second practical video about inference, and so we'll try to fit the model to data to the Apple prices. Thank you for watching, and bye.